All right, let's look at the next example. Consider a y prime equals dy to dx equals y times 2 minus y. Find the critical points. Critical points of this equation. And determine the stability of each of those critical points. Okay, for the answer, we know that for critical points, we need to set y prime equals 0. Critical points, let's set y prime equals 0. That gives y times 2 minus y equals 0. So this equation has obviously two solutions, y equals 0 and y equals 2. So we have two critical points. And now let's determine stability. So far, it was very straightforward. Now for stability, of y equals 0, let's start with y equals 0. So let y of 0, let's say equals 0 plus h. So this is my x0, which I chose as 0. And my y0, y naught is 0. So we have to see if we change the initial condition slightly, then what happens to the limit of the solution as x goes to infinity. If the initial condition is 0, if y of 0 is 0, then the solution will be y equals 0, constant function 0, and the limit will be 0 as well, of course. Because see, when we concluded that y equals 0 is a critical point, it also means that y equals 0 as a constant function is a solution for our equation, which we called it equilibrium solution. Now, if we change the initial condition slightly from 0, we change it to 0 plus h, this y equals 0 will not be a solution anymore. We will have another solution, but that another solution, we can still look at the limit of it as x goes to infinity. Is the limit of it as x goes to infinity still 0? In that case, we would call the critical point stable. Otherwise, we would call it unstable. So let y of 0 equals 0 plus h, with h being a small positive or negative number. And we want to find limit of y of x as x goes to infinity, where y of x is the solution of IVP above. So what is the equation? Y prime equals y times 2 minus y, and y of 0 is h. So here I can say that right-hand side is non-zero, because y of 0 is h, and I'm assuming h is a small positive or negative number, so it's non-zero. So we can say that, note that y is not equal to 0 because y of 0 is h, which is not 0. And y is not equal to constant function 2 as well. When we say y not 0, we mean it's not constant function 0, because at least at some point it's non-zero. And similarly, it's not constant function 2, because again, at some point is h, which is not 2. I can assume that h is not 2 because we said h is a small positive or negative number, so we can assume that it's not 2. Even if we had to assume that h is not 0.1, we could still make such assumption, because we could still assume that h is not 0.1 because we can consider h to be something smaller than 0.1, such as 0.01 or 0.001. Even if we had to assume that h is not 0.01, we could still make that assumption because we could assume that h is even smaller than that, like 0.0001. Okay, so this is the meaning of the sentence when we say h is a small positive or negative number. So we are allowed to assume that h is as small as we want. So y is not 0 and y is not 2. That means y times 2 minus y will be non-zero. And therefore, we can divide both sides. By y times 2 minus y. Then I'll have dy to dx equals y times 2 minus y. Therefore, dy divided by y times 2 minus y will be equal to dx. Now integrate both sides. Then I'll have integral dy over y times 2 minus y equals integral dx. That means if I use partial fractions to calculate the first integral, then I'll have 1/2 times integral 1 over y plus 1 over 2 minus y. I'm just guessing the coefficients here. You can write it as a over this plus b over this if you want, but if I use 1 in both of them, then the common denominator will be y times 2 minus y, numerator will be 2 minus y plus y, which is 2, then divided by 2 will be 1, and then dy equals integral dx is x plus c. Then I have 1/2 ln absolute value y minus ln absolute value 2 minus y equals x plus c. And that gives me ln a minus ln b is ln a over b. So ln absolute value y over 2 minus y equals 2x plus 2c. And that gives me absolute value y over 2 minus y equals e to power 2x plus 2c. And if I call this e to power 2c as d, then I'll have d times e to power 2x. And then I can say that y over 2 minus y will be plus minus d times e to power 2x plus minus d, if I call it f, then I'll have f times e to power 2x. And here f is a positive or negative constant. Because d is e to power 2c, which is positive constant, and f is plus or minus d, so f is a positive or negative constant. And now we can easily find y. We just need to cross multiply. Then we'll have y equals 2 minus y times f e to power 2x. And that gives me y equals 2f e to power 2x minus y times f e to power 2x. And if I isolate for y, in order to solve for y, let's take all y's into one side. Then I'll have y plus y times f e to power 2x equals 2f e to power 2x. And then y, if I take y out, y as a common factor, and then inside bracket, I'll have 1 plus f e to power 2x equals 2f e to power 2x. And then y will be equal to 2f e to power 2x divided by 1 plus f e to power 2x. So this will be the solution for our equation. And to find f, use the initial condition. Use the initial condition. Y of 0 equals h. Y of 0 will be 2f divided by 1 plus f. If I replace x with 0, y of 0 will be 2f over 1 plus f, and this is supposed to be h. Now we can easily find f from this equation in terms of h. Now I have 2f equals h times 1 plus f, which is h plus hf. So f times 2 minus h equals h. See, 2f is h plus hf, and I want to find f. So I need to isolate for f. I need to take all terms containing f into one side. So I took this term to left side. Then I got 2f minus fh, which can be written as f times bracket 2 minus h, and right-hand side remains h. And then f will be equal to h over 2 minus h. So substitute back now. And then I will have y equals, y was 2f e to the 2x. So 2f is this guy, h over 2 minus h e to the 2x divided by 1 plus h over 2 minus h e to power 2x. This is the solution of IVP above, initial value problem above. So we can now find the limit of y as x goes to infinity. That would be limit 2h over 2 minus h e to the 2x divided by 1 plus h over 2 minus h e to the 2x. X goes to infinity. Then if I divide top and bottom by e to the 2x, then I'll have limit 2h over 2 minus h divided by e to power minus 2x plus h over 2 minus h as x goes to infinity. Now as x goes to infinity, e to power minus 2x goes to e to power minus infinity. But e to power minus infinity is 0. So then I'll have, the answer will be 2h over 2 minus h divided by h over 2 minus h. And now 2 minus h cancels with this, h cancels with this. The answer will be 2. So we showed that limit y of x as x goes to infinity is 2, which is not 0. So that means y equals 0 is unstable. Y equals 0 is unstable. Because if it was stable, if y0 was stable, limit y of x as x goes to infinity must have been still 0. But it's not 0, so y equals 0 is unstable. So I remind you about the situation one more time. If the initial condition is 0, see, y equals 0 is a critical point. Therefore, if the initial condition is 0, and y equals constant function 0 is the solution, and the limit of y will be, of course, 0. Now, the question is, if we change the initial condition slightly, instead of 0, y of 0 equals 0, we would say y of 0 equals 0 plus h, where h is a small positive or negative number. Then what happens to the limit of the solution as x goes to infinity? We saw that if with the initial condition y of 0 equals h, the solution will be this function. So when I say solution of IVP above, I mean the solution of IVP y prime equals y times 2 minus y with y of 0 equals h. The solution will be this function, which is a function totally different than 0. If the initial condition was 0, solution would be y equals 0. If the initial solution is y of 0 equals h, the solution will be this. Now, what happens to the limit of the solution as x goes to infinity? We saw that the answer will be 2, not 0 anymore. So that means y equals 0 is unstable. So this is very interesting. See, if we still have the same differential equation, let's consider this differential equation. One time you consider this differential equation with y of 0 equals 0. Then the limit of the solution as x goes to infinity will be 0. Another time you consider this differential equation with initial condition y of 0 equals, let's say, 0.000001, a very small number. Then the limit of the solution as x goes to infinity is suddenly 2. So as x goes to infinity, the solution will be in a completely different place, even if it's very slightly changed the initial condition. So I can make the comparison like, again, like raising children or how to behave with children. If you change the how you raise your children very slightly, the final outcome of that child when he is, for example, 50-year-old, could become totally different. So this is similar to that in that sense. If the initial condition is 0, then the limit will be 2. But if we very slightly change the initial condition, the final behavior of the function is now totally different. Okay, guys, so this is about stability of the first critical point that we determine is unstable. What about the second critical point? So for second critical point, y equals 2. So let's consider the IVP. Again, the equation is still same, y times 2 minus y. This time with the initial condition y of 0 equals 2 plus h. We need to solve this IVP and look at limit y of x as x goes to infinity, where y of x is the solution of IVP above. We need to solve this IVP and look at the limit as x goes to infinity. If this limit remains 2, because we know that if the initial condition is exactly 2, then the limit will be 2, because y equals 2 is a critical point. Now the question is, if we slightly change the initial condition, let's say instead of 2, I can say 2.00001. Is the limit still 2? In that case, we would say y equals 2 is stable. But if the limit as x goes to infinity suddenly changes, like the previous case, it suddenly changed, the limit suddenly changed from 0 to 2. It jumped from 0 to 2, even if it's very slightly changed the initial condition. In that case, we would say the point is unstable. So let's solve this equation and find the solution, and let's look at the limit of the solution as x goes to infinity. Okay, again, like previous case, based on the initial condition, we can say that the right-hand side is non-zero. So since y of 0 equals 2 plus h, we can say y is not constant function 2 and y not constant function 0. See above, so we can divide both sides by y times 2 minus y. And then we'll get dy over y times 2 minus y equals dx. And then again, integrate both sides. And solve for y. Then again, see above, because the calculation from here will be similar to what we did above. In above, we also solve the same equation. See, integral here, dy over 2 minus y times 2 minus y equals dx, which is exactly what we have here. So then we will have our final answer will be y equals, what was it, f 2f e to 2x 2f e to the 2x 1 plus divided by 1 plus f e to the 2x. And to find f, use the initial condition. Our initial condition is y of 0 equals 2 plus h. Instead of y of 0 equals h, this time is y of 0 equals 2 plus h. So still will be, the final answer will be still the same. Instead of h, I need to replace it with 2 plus h. Because previously this answer was obtained based on the assumption that y of 0 was h. But now my initial condition is y of 0 equals 2 plus h. So everything is still the same. I just need to replace this h here with 2 plus h. So it will be 2 times 2 plus h, and here replace h with 2 plus h. It will be 2 times 2 plus h, and this will be minus h, 2 times. So y will be 2 times 2 plus h divided by minus h e to the 2x divided by 1 plus 2 plus h divided by minus h. Here also I replace h with 2 plus h. And then I got this times e to the 2x. So now if I divide again both sides by e to the 2x, divide top and bottom by e to the 2x, then I'll get 4 plus 2h divided by minus h e to the 2x divided by e to the minus 2x plus 2 plus h divided by minus h e to the 2x. Sorry, e to the 2x I've divided by it. So plus this number. And this one also will be 1 because I'm dividing top and bottom by e to the 2x. So this will cancel, and this will be replaced by e to the minus 2x. Now I can find the limit as x goes to infinity. So limit y of x as x goes to infinity will be limit this function here, 4 plus 2h divided by minus h divided by e to the minus 2x plus 2 plus h divided by minus h, x goes to infinity. And what will be this limit? Well, e to the minus infinity, we know it's 0. E to the minus infinity, we know it's 0. So this limit will be 4 plus 2h divided by minus h divided by 2 plus h divided by minus h. And then this will cancel with this. And 4 plus 2h divided by 2 plus h is simply 2. So we showed that limit y of x as x goes to infinity is 2, where y of x is the solution of IVP, y prime equals y times 2 minus y, with y of 0 equals 2 plus h. So that means y equals 2 is a stable critical point. So if y of 0 was 2, then the limit would have been 2 because the solution would have been the constant function 2. Now, if the initial condition, instead of 2, we slightly change it to 2 plus h, let's say to 2.001. The limit is still 2. We just showed that the limit still will be still 2. So that means y equals 2 is stable, because if we slightly change the initial condition, nothing happens to the limit. The limit would remain stable, and we would call the critical point a stable critical point. Now, let me give you an exercise that you can think about it. So here we had 2 critical points, one stable, one unstable. And, you can do a similar exercise. Let's say exercise, find the critical points of y prime equals dy to dx equals y squared, and determine their stability by finding the solution of IVP, where you slightly change the initial condition. So the critical point here, let me give you a hint. The critical point is just y equals 0, because right-hand side, if you set right-hand side equals 0, you will have y equals 0. Now, if the initial condition is y of 0 equals 0, then the limit will be 0, of course. But if you slightly change that initial condition from y of 0 equals 0 to y of 0 equals 0 plus h, let's say, if h is a small positive or negative number, can we still say that the limit of the solution will be still 0? In that case, if that happens, then you would call your critical point y equals 0 stable. But if the limit would suddenly change, if the limit suddenly changes, then that means the critical point is not stable. Okay, guys, so this was about the concept of stable and unstable critical points and autonomous equations. We did some examples, and I left one as exercise, where I can include more in the assignments. Now let's move on to the next topic. So next topic 1.7, and numerical methods. Numerical methods, Euler method. Numerical methods and Euler method. So here, let me explain about the problem. So given a first order ODE, of the form y prime equals f of x and y. Y prime equals f of x and y with the initial condition y of x naught equals y naught, Our goal is to estimate, we want to estimate y at some point x1, where y is the solution of IVP above and x1 is not equal to x naught. So this is basically called a numerical method where we estimate the value of a function at a given point. You have seen some numerical methods before in Math 113 that, you know, for example, linear approximation, where you estimate the value of a function at a point. So here we have this initial value problem, y prime equals f of x and y with y of x0 equals y0. We want to estimate y at some point x1. Then you may ask me, why do we need estimate? Well, if we have this IVP, we know that this IVP, it's a first order differential equation with one initial condition. But then under certain condition, it will have a unique solution. Then why don't we find the solution? And then once we have the solution, we can simply replace x with x1 and find the exact value of y of x1 rather than just an estimate. Well, the answer to this question would be sometimes, you know, it's hard to find the exact solution of a differential equation. Depending on what type of function we have here, it could be very hard or long to find, you know, the exact solution, or sometimes even impossible to find the exact solution. And that's why we need to have numerical methods in the case that it's hard to find the exact solution, or in the case that it could be even impossible to find the exact solution, then we need to have at least some estimation for our solution at some point. So the reason, or let me say that, note that numerical methods and estimating y of x1 is necessary, since in some cases it is very hard or sometimes impossible to find the exact solution. Exact solutions, and hence finding exact values, exact value of y of x1 could be hard or impossible, depending on the type of ODE, depending on the type of the given ODE. All right. Now, in order to find estimation for y of x1, we want to use the idea of linear approximation that you have learned before in Math 113. So let me remind you about what you learned in Math 113 about linear approximation. All right, so recall from Math 113, linear approximation. Linear approximation. So how could we do a linear approximation for a given function around a given point. So let f of x be a differentiable function. And let x equals a be in domain of f. So let's look at the graph. Let's say this is a differentiable function, and this a is a point on the graph. Then we can approximate the values of f of x for x close to a using the tangent line at x equals a. So let's say this is a tangent line at x equals a. And as you can see from the graph, the values of f of x and the tangent line are close to each other if x is close to a. So let's say this, look at this x value close to a. This is f of x. And this one here is L of x. So this is what it calls f of x. This is L of x, the equation of tangent line at x equals a. So the original function and the tangent line, they're close to each other as long as x is close to a. So for this reason, we can approximate the values of f of x if x is close to a using the tangent line at x equals a. So what was the equation of tangent line at x equals a? Equation of tangent line at x equals a. So how can we find the equation? Y minus f of a equals f prime of a times x minus a. This is the equation of tangent line at x equals a. So we can say that y is equal to f of a plus f prime of a times x minus a. So this is basically the formula or the equation of tangent line at x equals a. And this is what we called it here in this graph as L of x. So this is basically our L of x. So we can say f of x is almost equal to L of x, which can be written as f of a plus f prime of a times x minus a, if x is close to a. Okay, so now our f of x here is basically the solution for the differential equation. So back to our case. What do we have? We have y prime of y prime equals f of x and y. And basically y of x naught equals y naught. Now let y equals g of x be the solution for this IVP, initial value problem. Then we can say that g of x is almost equal to, now I want to apply this formula, and instead of f, I have g. Okay, this f here has nothing to do with this f. This f is a function of one variable. This f is a function of two variables. So our f in our case is g. So I have to replace this f with g, small g. So g of x almost equal to g of a plus g prime of a times x minus a. And what is a? In our case, a is x naught. This x naught is my a, and this g is my f. So we can say g of x is almost equal to g of x naught plus g prime of x naught times x minus x naught. Now, what is g prime of x naught? See, g is the solution for this equation. So g prime of x naught is going to be f of x naught and y naught. So since g of x is the solution for IVP above, we can say that g prime of x naught is equal to f of x naught and y naught. So when we say g is a solution for this equation, means if we replace here, replace y with g here, then the equation will be satisfied. So maybe I can write it this way. So if, because it's a solution, then we can say g prime of x is equal to f of x and g of x. See, I just rewrote this equation and just replace y with g. So g prime equals f of x and g. And now if I replace, well, this is supposed to be true. This equation holds for every x. True for every x. So if I replace x with x naught, then I'll get g prime of x naught equals f of x and g of x naught. G of x naught, well, again, because g is the solution for this equation, again, I can replace y with g. So g of x naught will be y naught. So g of x naught is y naught. So I can say g prime of x naught is equal to f of x naught and y naught. Here I replace x with x naught. So x naught here, x naught here, x naught here. And g of x naught is y naught. So this will be, this is how g prime of x naught can be computed. So I can replace it here, substitute back. Then I'll get g prime of x naught, I'll get g of x almost equals to g of x naught plus f of x naught and y naught times x minus x naught. And finally, our goal was to find y of x1, and I called it g here. So g of x1. So let's replace x with x1, and then we get g of x1 almost equal to g of x naught plus f of x naught and y naught times x1 minus x naught. And g of x naught is y naught. So we can say y of x1 equals g of x1 almost equal to y naught plus f of x naught y naught x1 minus x naught. All right, so what about if x1, if x1 is close to x naught, we can use this equation. But what about if x1 is not close to x naught? Then how can we use this equation? Well, we can reach x naught, x1 in that case in few steps. So let's say if x naught, for example, is 0 and you want to reach, for example, 4. Well, we can do it in few steps. For example, our x1 could be first 0.5. So first we can calculate y of 0.5. Then using that, we can go to another 0.5. Then we will find 1. Then we will find 1.5 until we reach 4. So we can define a step size, which we can call it h, by dividing the whole interval from x naught to x1. We can divide it into n equal subintervals, and we can go from x naught to x naught plus h, then from x naught plus h to x naught plus 2h until we reach x1. So if x1, or if you say note that if x1 is not close to x naught, then we can divide the interval from x naught to x1 into n equal subintervals and using the value of y of x naught. First, we estimate y of x naught plus h. Then y of x naught plus 2h, then y of x naught plus 3h, all the way to y of x naught plus nh. Here, h is x1 minus x0 divided by n. So here is a picture x naught. Then we go to x naught plus h. Then we go to x naught plus 2h, x naught plus 3h, all the way to until we reach x1. Why are we doing this? Because, we want this x1 here is supposed to be close to x naught in order for us to be able to apply linear approximation formula. For linear approximation, we need x to be close to a. But if in the question x1 is not close to x naught, or if it is close, but we want a better estimation, because if you use a smaller step size, you will have better estimation. So if x1 is not close to x naught, or if it's close, but you want to have a better estimation, we can divide the interval from x naught to x1 into n equal parts. And h is the length of each subinterval, which is usually a small number. Then x naught plus h will be close to x naught. So we can apply linear approximation formula to estimate y of x naught plus h. Then we can estimate y of x naught plus 2h all the way to the last step will be x naught plus nh. What will be x naught plus nh? Well, h is this formula, right? So nh will be x1 minus x naught. X naught plus that will be x1. So x naught plus nh is same as x1. So the last step is to estimate y of x1, which is our final goal. So let's look at an example now. An example, let y prime equals y squared with y of 0 equals 1. Estimate. Okay, this method here is called Euler method. So maybe I can mention that here as well. The method described above to estimate y of x1 is called the Euler method. So now let's look at an example. Let y prime, let y prime equals y squared with y of 0 equals 1. Estimate the value of y of 2 using step size h equals 0.5. Or I could ask, or using n equals 4. N equals 4 sub-intervals. Compare your estimation with the exact value of y of 2. So I want to have an estimation for y of 2 and compare it with the exact value. Okay, so the step size, if the step size was not given and n was given, we could still easily find step size. Step size is the difference between x1 and x naught divided by n. So 2 minus 0 divided by 4 is 0.5. So in the exam, I could give you h, or equivalently, I can give you n. Doesn't matter. If I give you n, you can still find h. So here we have 0 here and 2 here, and then 0.5 here, 1 here, 1.5 here, 0.5, 1, and 1.5. So we have to go from 0 to 0.5, then from 0.1 to 5 to 1, from 1 to 1.5, and from 1.5 to 2. So using Euler formula above, we can say that y of 0.5 is almost equal to, so before Euler formula, I mean this formula. formula star. Y of 0.5 will be y0 plus f of x naught y naught times 0.5 minus x0. And x0 here is 0, y0 is 1. So this will be 1 plus f of 0 and 1 times 0.5 minus 0. And f of 0 and 1 is 1, because you know f of x and y in our case is y squared. So you look at the right hand side, f of x and y is y squared. So f of 0 and 1 is 1. So this is going to be 1 plus 1 times 0.5 minus 0. And this is 1.5. So first we found an estimation for y of 0.5, which is 1.5. Then we need to find an estimation for the next step, which is 1. So we already found the estimation for y of this point. Then we need y of this point, then y of this point, then y of this point. Now, what will be the estimation for y of 1? So y of 1 almost equal to y of 0.5 plus f of 0.5 and y of 0.5 times 1 minus 0.5. Using formula star with this time x naught, our x naught here, we have to replace it with 0.5, and y naught will be y of 0.5. So we can still apply this formula, but our x naught and y naught are not the original x naught y naught, because we use the original x naught y naught to find the estimation for the function at 0.5. So we started from here using this starting point. We found the estimation for y of 0.5. Now that we find the estimation for y of 0.5, this is now our new starting point. So forget about the original starting point. Now this is our new starting point. We have to use this new starting point to find the estimation for the next point, which is y of 1. So the starting point must be replaced by 0.5 and y of 0.5 instead of x naught, y naught. Y naught was y of, what was in the formula? Y naught is y of x naught. Now this x naught is replaced by the new starting point, which is 0.5. So the y value will be also replaced by y of 0.5. And then 1 is the new point minus the new starting point, which is 0.5. Y of 0.5 was almost equal to 1.5 plus, now f of 0.5 and y of 0.5 is same as f of 0.5 and 1.5. And y of 0.5 is 1.5, and f of 0.5 and 1.5 is 1.5 squared, because f of x and y is y squared. So 1.5 plus 1.5 squared times 0.5. And then this is 1.5 times 1 plus 0.5 times 1.5. So this is 0.75, this is 1.5. Times 1.75. And this will be 2.625. Now that you find the value of estimation for y of 1, we can now find the estimation for the next point, which is 1.5. Next, find the estimation for y of 1.5. Then, so let's leave this part as exercise. And then again, find the estimation. Then using y of 1.5, find the estimation for y of 2. See, when you want to find estimation for y of 1.5, again, you have to use the formula star. Formula star, but this time, instead of y naught, you have to use y of 1 and f of 1 and y of 1, because this is the starting point. Our new starting point will be at 1. In order to estimate at 1.5, our new starting point is at 1. So we have to, instead of using y naught, we have to use y of 1. And if instead of x naught, we have to use 1. Again, instead of this y naught, you have to use y of 1. And then x1 minus x naught will be 1.5 minus 1. So this way you will find an estimation for y of 1.5. Once you have estimation for y of 1.5, you can find y of 2. How can we find y of 2? Y of 2 will be, again, this one we have to use, if you want to find y of 2, here we have to use the new starting point, which is the y value at 1.5. So y of 1.5 plus f of 1.5 and y of 1.5 times 2 minus 1.5. So just do these calculations and find the estimation for y of 2. And then the next part of the question is compare with the exact value of y of 2, which I can leave as exercise. So this is a separable equation. This is a separable equation. You can easily solve it. And find the exact solution. Once you have the exact solution, you can find the exact value of y of 2. Compare it with your estimation that you found in the previous part. So if you want to have a better estimation, if you want to improve your estimation, you can, of course, use a smaller value, smaller step size. So right now we use h equals 0.5. For example, if you use h equals 0.1 instead of 0.5, use 0.1, then the calculation will be longer, because if you want to reach 2 using 0.1, first you have to go from 0 to 0.1, then 0.1 to 0.2, then 0.2 to 0.3. So there will be 20 sub-intervals, 20 steps. So it will be longer, but your estimation will be better. You also try that, use h equals 0.1, and then you'll see that you will have a better estimation. Let me give you also one exercise, another exercise. Use the Euler method above. To estimate y of 3 if y prime equals 3x plus 4 y cube with y of 1 equals -2, and use a step size h equals, let's say, 0.4. So you can start from 1 here, and then you go to 1.4, then you go to 1.8, then you go to 2.2, 2.6, and then you go to 3. So using the starting point 1 and -2, and this is your f of x and y here, 3x plus 4y cubed is your f of x and y. You can estimate the value of y of 1.4. Once you have the estimation for y of 1.4, then that will be your new starting point. Using that, you can estimate y of 1.8 and so on. Now, the difference between this question and the previous example is that previous example was very easy to find the exact solution. It was a separable equation. But this question is not, finding the exact solution is not as easy as the previous one, but we can still easily find an estimation for y of 3. So you can see that numerical methods and Euler method in particular could be very helpful, especially if we cannot find the exact solution, or if finding the exact solution is hard. In those cases, we can easily use Euler method to at least find an estimation for y for any of the solutions evaluated at any point. We can find the estimation for y of any point without finding the exact solution or without solving the equation algebraically, basically. Okay, guys, so this was about Euler method and numerical methods to find estimation for the solutions of a differential equation evaluated at an arbitrary point. Okay, guys, so thank you and see you next time.